In this video, we'll talk about parabolas from a conic sections approach. In order to do that, we should remind ourselves what a parabola is, and in order to do that, we need to remember what a quadratic is. So remember that a quadratic is just a second degree polynomial, and if we have a quadratic equation, it would look something like this. This is the most basic possible quadratic equation, y equals x squared. If we wanted to complicate it a little bit, we could put an a out in front of the x squared. If we change that value of a, what we would be doing is making this parabola, because the graph of a quadratic is a parabola, we'd be making it either more stretched out or more compressed, depending how you think of that. And we could also, if it was negative, we could also flip it upside down and stuff. But there's all sorts of things that could happen as far as transformations of functions. That could be something like this. If we had y equals ax squared plus bx plus c, well, this can encompass all the possible, every possible parabola, essentially, every possible functional parabola at least. And by itself, this isn't that important. But if we set this equal to 0, so if we said 0 equals ax squared plus bx plus c, well, now we have the a, b, and c necessary to solve the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And this we learn is useful for finding the values for x that make y equals 0. So essentially they are x-intercepts, and we kind of think of those as solutions to a quadratic equation, even though that's not technically the right term, because an x-intercept and a solution are not necessarily the same thing. We learned that some quadratics are kind of just floating and they don't cross the x-axis at all, yet they still have solutions. So uh, we use a quadratic formula for that at first. We also develop our factoring abilities, and we end up with something that looks like this. This is like the factored form of a quadratic, and this is useful because x equals m and x equals n would be the two values that gave us a 0. If we set that equal to 0 and use a zero product property, we'd find that x equals m and x equals n correspond to the x values of the x-intercepts, or the solutions to the quadratic. And then the last version of a quadratic that we look at is the vertex form. So y equals a times x minus h quantity squared plus k, where the vertex is at the point h comma k, and also the axis of symmetry is at x equals h. And this is all for parabolas that open up and open down. But all of these were useful for different reasons. And certainly we're going to use primarily the vertex form when we're talking about conic sections. But we add a little bit of detail to that. And the detail that we add to that is based around what we need parabolas for in real life. So here's some examples. And I'm not mentioning one of my favorite applications of a parabola, which is like a suspension bridge, because it doesn't really the thing that we're looking for isn't really super relevant for like a bridge design. But here's three examples of concentrated solar power, and these are different designs. This first one is like a parabolic trough kind of style where light comes in at this, basically perpendicular. You can imagine if it was a plane from there to there, bounces off this reflective surface and then kind of focuses back, no matter where it started, on this little center pipe, and that pipe is carrying something that absorbs heat, and then we use that heat to generate electricity. We also have these. This is Ivanpah. You can Google that. It's in the California desert near Las Vegas, which is not in California. But anyway, the light comes down from outer space, the sun, and bounces off these mirrors that are arranged in just a big flat parabola, essentially, that bounce it up and to concentrate on this focal point, and all that heat energy is stored and then used, not stored, but temporarily stored and used to generate electricity. And then we have also these things called Fresnel lenses, which Fresnel lens, the best way for me to describe that is imagine one of those magnifying sheets that maybe like your grandparents have. And they're so cool. Like they cost $1 at the dollar store, but they're so cool. It's basically a parabola that's just been cut a whole bunch of times and flattened down. And it magnifies things. And you could, use it to magnify things or concentrate light on a specific point to maximize the efficiency of a solar cell, which is really cool. You also probably every day see some kind of satellite dish. Maybe there's one on your house or your neighbor's house or something like that. And these are also parabolic. They have a parabolic kind of reflecting surface where some sort of signal, and in a lot of cases it's like a radio wave, will bounce off of this dish. And the satellites, the telescopes that you think about in big observatories also are called reflective reflective telescopes because they have a big parabolic mirror, and that mirror then reflects light onto a sensor. Essentially, it is all kinds of actually extremely interesting math and design principles behind telescopes. But these ones work by reflecting off this parabolic dish into this kind of focal point that has another little secondary reflector, and then it bounces back down into this thing called what's it called, a feed node. I can't remember exactly what it's called, but it's like an antenna in it, and it processes the signal and stuff. We also have this is called the FAST telescope. You can Google that. It's in China, and it's this gigantic radio telescope. It's so cool. All these little panels can move, which actually brings me to my final example of parabolas. And the most common one in the world is the ones in your eyeballs. So lenses, optical lenses are often, well, usually parabolic in nature. The ones in your eyeballs are unique in that they can actually change their shape all the time. When you focus on something that is a certain distance away and then you kind of change your focus to something closer, the actual shape of the lens in your eyeball changes, which to me is simultaneously fascinating and extremely disgusting, which is why I'm not showing a picture of it, because it gives me kind of the heebie-jeebies. But super interesting anyway. All of these things what they all have in common. It's that we're really interested in knowing where the focus of a parabola is. Let me show you kind of what I mean. So if we have this diagram right here, let me zoom out a little bit. I'm going to grab this point on this parabola. You can see that if I change where the focus is, so the focus is this red dot. If I move it farther away from the vertex, then what happens is we get a kind of a wider parabola, right? If I move it closer to the vertex, then we get this like more skinny parabola. So there's a relationship clearly between where the focus is and how wide or how fat the parabola is, which we also know is the letter A in the vertex form or any of the forms of a quadratic. That also has an impact on that. What's cool geometrically about a parabola is that if you had rays coming in from somewhere, some source, they will bounce off because of the geometry right to the focus, which that is why we're so interested in knowing where the focus of a parabola is. So our study on parabolas and conic sections is oftentimes focused on finding where the focus is. So how do we do that? Well, mathematically it kind of looks like this. If I had a point, and this point is the focus, we'll call this the coordinates of this point 0, p. Okay, 0, 0 is right here, 0, 0. So 0, p would just be p units up from the vertex, and p is what we use for focal length when we're talking about conic sections oftentimes. Okay, then I have any point on the parabola xy, so we'll call this xy. There exists a line called the directrix line, and the directrix line is kind of I don't know how to really describe this. It's just in a functional parabola, so one that opens up or down, we have a horizontal line, and if you drew a line from the focus to the vertex, the directrix would be perpendicular to that line. So if that line we're talking about is vertical, the directrix would be horizontal. If it was horizontal, the directrix would be vertical. The geometric definition of a parabola is it's a set of all points that are equidistant from the focus. So a set of all points that are equidistant from the focus. So like from here to here, and the directrix from here to here. So like if this was D2 and this was D1, what the geometric definition of a parabola is that D1 is equal to D2 for any point that we chose, xy, on that parabola. So we actually can figure out the equation or how specifically P is related to A in our quadratic form, in our equation for a quadratic, or just a quadratic equation generally, if we say this is y equals ax squared. So if that's y equals ax squared, we have a way of calculating the distance each distance d1 and d2. So d1, the distance formula says it's the difference in the x coordinates between those 2 points. So in our case, x minus 0, quantity squared, plus the difference in the y coordinates. So in this case, y minus p, quantity squared. Okay. We also have this point down here because this is vertical. So if that's the case, then this coordinate would be x comma negative p, because remember the definition means if this is p, then the distance here is also p, because the vertex is also a point on the parabola. So that's that coordinate point. So if we now look at d2, it's the square root of the difference in x value squared, so x minus x, quantity squared, plus the difference in y value squared, so y minus negative p is y plus p, quantity squared. If we squared both sides to ignore the square roots, what we'd end up with is this, x squared plus y squared minus 2yp plus p squared equals 0 squared plus y squared plus 2yp plus p squared. We can cancel out the p squareds because we would subtract p squared from both sides, subtract y squared from both sides, and if we added 2yp to both sides, I don't know, y to up, then we would have x squared is equal to 4yp. And if we solve this for y, we would get that y is equal to 1 divided by 4p times x squared. Now, if we compare that to our original equation, we have y equals ax squared, and knowing that this is the same equation, then that means that 1 over 4p must equal a. So a equals 1 over 4p, and sometimes more usefully, p is equal to 1 over 4a if you just solve for p instead. So this is really significant. This is the relationship between a and p is something we're really interested in knowing because it's where the focus is. It's the focal length of a parabola. Also, if we use this information and do a little bit of substitution, so recalling that y equals a times x minus h quantity squared plus quantity squared plus not working plus k is the vertex form of a parabola. If we substituted 1 over 4p in, we'd have y equals 1 divided by 4p times x minus h quantity squared plus k. My pen doesn't seem to be working, which is not great. If I subtract k from both sides and multiply both sides by 4p, I'll have this. 4p times y minus k is equal to x minus h quantity squared. And this is a really useful version of the quadratic equation, also the equation of a parabola. The other thing to know is that this is just for an up and down parabola. If we had one that went left or right, it would be a little different. We would start with x is equal to a times y minus k quantity squared plus h. And if we do our same substitutions here, that's an h. Let's just pretend that's an h. It's not erasing well, okay? And then if we did the same thing, we'd end up with this. 4p times x minus h is equal to y minus k quantity squared. So the equations we'll be working with are this one and this one, but then also sometimes this one and this one, which are the same thing. It's just using p instead of a or vice versa. So anyway, how do we use all this math to apply it to a problem that we would get in a pre-calculus class? So happy you asked. A lot of times we want to graph stuff. And unfortunately, because math can never be super straightforward, we're given a equation that doesn't really suit our needs as far as what we need in order to graph. What's the easiest way to graph a parabola? The easiest way to graph it would be to find the vertex. And then from there, we got a little bit of stuff we can do and anyway, proceed. But this isn't in vertex form, so we need to get it into vertex form. The first thing to do is identify what's the thing being squared. It's x squared. So this is going to end up looking like this. We're going to write an equation that looks something like this. And in order to get what we have into that form, we need to complete the square. So first step would be to get everything that's not the y onto one side. So I have 8y is equal to x squared plus 4x minus 4. And I need to complete the square on the right side of this equation. So I'm going to say 8y is equal to x squared plus 4x plus something, and then have the minus 4. Now, I want to make a perfect square trinomial right here. That's what completing the square is. In order to do that without without bogging you down with all the real geometric details about how this works, you take the coefficient of the middle term, which in this case is 4, you divide it by 2, so you get 2, and then you square it, so you get 4. That means I have to add 4 to the right side of the equation. Now, it's algebra, so I have to maintain balance here. If I add 4 to the right side of the equation, I also have to add 4 to the left side, or if I add 4 to the right side, I also have to take 4 away from the right side, which kind of doesn't make sense. It's sort of weird. But that's what we do. Now, what does this enable? Well, 8y equals, the whole point of doing this completing the square was being able to rewrite this perfect square trinomial as a perfect square of binomial. And then we have minus 8. And we just want to solve for y, so we divide everything by 8. And we'd have this. Y is equal to 1/8 times x plus 2 quantity squared minus 1, which gives us everything we need to know, because the vertex hk is, just for this one, -2, -1. And the axis of symmetry, by the way, is would be x equals -2. I'm not don't really care that much about this right now, although it's important to know that the focus and the vertex are always along the axis of symmetry. But we want to know the focus. And what I would recommend here is to kind of sketch your parabola first. So I know the vertex is at -2, -1. And I know it opens up and down. So that means my focus is have to be somewhere inside the parabola. That's how the focus is oriented. So I'm going to need to add some value p to the y value of my vertex in order to find the focus. In fact, this is like the equation. If we have an up and down parabola, h, k plus p is the coordinates of the focus. So for us, it would be, for this problem, it would be -2 and then -1 plus, oh, we don't know what p is, sorry. We get p is equal to 1/4a. So p would equal 1 divided by 4 times 1/8, which is just going to be 2 after you simplify that. So p is 2, so we're going to add 2 to -1 and get 1. So that means, let me erase all this stuff. We had our vertex right there. Our focus is at -2, 1 right here. And our directrix is just going to be, remember, it's equidistant from the directrix and the focus are going to be equidistant from the vertex. So if I went p up to get to the focus, I'm going to go p down to get to the directrix line. So it's going to be y is equal to effectively k minus p, which for us is -3, right? We had -1 subtract 2 is -3. So we have this horizontal line be represented as a dotted line like this. Okay, there's one other thing forgot to mention here. On this diagram, if I had specifically chosen a point that was horizontally away, so if I had chosen this point right here as my point that was on the parabola, then the coordinates of this would be x, p. And if I had done all of this math with x, p instead of x, y, you would find at the end of it that x is equal to 2p. Okay, and x is the horizontal distance from this focus to where that horizontal line would intersect with the parabola. So we can say then that that distance right there is 2p, and if it's 2p that way, it's 2p that way. So this actually has a name. From here to here has a name. It's called the lattice rectum of a parabola. And if we have that information, meaning if we go left or right 2p from our focus, so p was 2, so if we go 4 over, there's a point on the parabola right there. There's a point on the parabola right there. Then we've got 3 points on our parabola, and if we kind of are pretty familiar with how a parabola is drawn, that's going to be good enough for graphing it. So it's going to go like this. Okay. So there we go. We've graphed the parabola, we found the focus, and we have the equation of the directrix line, which is y equals -3. And we have, we obviously have our equation of the parabola too, which is useful also. Let's look at another example here, but this one will be a horizontally oriented parabola. We know that it's a horizontally oriented parabola because the y values are being squared here, or the squared term is y. So I'm going to do the same thing, but my ultimate goal is going to get it into this form. X equals a times y minus k. My pen is messing up here. Y minus k quantity squared plus h. Okay, so if I need it in this form, that means I'm going to need to complete the square, but this time with the y values. So I'm going to get the 12x by itself, and everything else will be on the other side. So I'll have 12x is equal to y squared minus 6y plus 21. 12x is equal to y squared minus 6y. I'm going to leave a little space. And notice that I'm going to have to add 9 in order to make those first three terms a perfect square trinomial. And then I'm just going to subtract 9 also to balance the equation. This allows me to rewrite as 12x is equal to y minus 3 quantity squared, and then 21 minus 9 is a number. I believe it's 12. If we divide everything by 12, we'll find that our equation in vertex form is x is equal to 1/12 times y minus 3 quantity squared plus 1. Now, why don't we find p, because we screwed up last time. P is equal to 1 divided by 4a. So a is 1/12, so this would be 1 divided by 4 times 1/12, or 1 divided by 4/12, which is just 3. So p, the focal length of this parabola, is 3. So what does that mean for us? First of all, the vertex of this, which is hk, right, is going to be, remember looking back up at our form, is going to be 1, 3. That's the vertex. Our directrix line, well, actually, let's come back to the directrix. Well, we'll write it and then we'll come back to it. The directrix line, if we remember from our previous example, we were adding values to the y value. We're adding p to the y value to find where the focus was. Here we actually added, we're going to actually want to add, well, we didn't do the focus yet. Let's go back to the focus, sorry. Focus, the vertex is at 1, 3, okay, right here. Because this is going to be a left and right parabola, we're going to want to add p to our h value instead of our k value. So for the focus for our left and right parabola, it's going to be h plus p comma k, which for this problem is just going to be 4, 3. That's where the focus is. And then the directrix line, because we added p to h, directrix. My pen is not working very well right now. We're going to subtract p from h. So we're going to get the directrix line of x now, because it's vertical, is equal to -2. So let's put that on the graph. We had our focus at 4, 3. So right here, our directrix line is going to be a vertical line at x equals 3. So something like this. Since p is 3, 4p is 12. Our lattice rectum is 12 units long, which means I'm going to go 6 up and 6 down from the focus. So 1, 2, 3, 4. I have a point on the parabola right there. I have a point on the parabola right there. I believe I counted 6 correctly. And now if I drew it, it would just look like this. So, this here, that distance is p, which is 3 for us. And this distance right here is 4p, right? That's 4p is the length of the lattice rectum. So we can have 3 points on a parabola, the vertex and the endpoints of the lattice rectum. All right, now we also are given problems sometimes where we don't want to graph it, but we want to find out what the equation is. And this is actually really straightforward, and I would recommend in every situation like this that you draw a picture. So these graphs are not here to draw the actual parabola, but to draw a picture. So if I plotted what was given to me, it would be this. It says that this one has a focus at 5, -2. So 1, 2, 3, 4, 5, -2. And the directrix line is at x equals -1. So it's a vertical line at -1. Now this actually tells me that, first of all, I know that the vertex is in the exact middle of the focus and the directrix line. So if I have a six squares here, so right in the middle, right there, that's the vertex. Okay, that point is the vertex, and it's at, what is that, -2, no, 2, -2. Okay, so HK is just 2, -2. Cool. And then we have, we also can find P, because P is just this distance, right? This is P. So P is equal to 3, and we need A. In order to write this equation, because it's a left and right parabola, this is going to be x is equal to A times y minus k quantity squared plus h. What do we have already? we have h and k, and we just need a. So a, we have p, we can find a. A is equal to 1 divided by 4p. That's 1 divided by 4 times 3, which is 1/12. So I have everything I need. The equation of this parabola then is x is equal to 1/12 times y minus k. K was -2, so plus 2, quantity squared, plus 2. Cool. That is the equation of that parabola. You could also graph this in like Desmos or something and verify that that's correct. Okay, how about the next one? So again, we're given information. We should plot it right away. We have our vertex at 7, 3. So 1, 2, 3, 4, 5, 6, 7. I think here's 7 and 3. So right there. And then our focus is at 7, 5. So up here. So our vertex and our focus are p away from each other. So right away, just by looking at it, I know that p is equal to 2. This is an up and down parabola because those 2 points are on the axis of symmetry. Y is equal to a times x minus h quantity squared plus k. That's the format I'm looking for. And I already have, I can get a because a is equal to 1 divided by 4p, which is 1 divided by 4 times 2, which is 1/8. So if a is 1/8, I now just need the vertex, and the vertex is given me, it's already given me as 7, 3, right? So hk is 7, 3. And I just write my equation out. Y is equal to 1/8 times x minus 7 quantity squared plus 3. And I'm all done. Now, it's really not a lot more complicated than that. One thing that could potentially happen that would make it a little more complicated is given the vertex form of a quadratic, and let's say you were given the vertex or something, or maybe you could be given the focus, the directrix, and then just a point. Oh, actually, that would be, you'd already have everything. Maybe you're given the vertex and a point on the parabola. That actually is enough to solve this, because if you were given the vertex, you'd have h and k, and if you were given a point, you would have x and y, because all this equation is even describing in the first place is a set of all points, x, y points that meet these criteria. So you would just be able to solve that for a and then rewrite the equation with a as the number it equals. Anyway, hopefully this was a pretty useful video. There's a lot of information here. I really enjoyed parabolas. I really enjoyed the other conic sections too, and I hope that this video maybe made you do that as well.